What if I told you that the outfit an astronaut wears during a spacewalk costs $150 million? That's more expensive than an F-35 Lightning II fighter jet, one of the most advanced warplanes ever built. We're talking about a single suit, a piece of clothing. And NASA only has 11 of them left, with just 4 ready to fly. But here's the truly mind-bending part. In 2025, these 40-year-old suits cost $150 million per year just to maintain. So why does a spacesuit cost more than a fighter jet? The answer will change everything you thought you knew about space exploration. Let me put this in perspective. An F-35A fighter jet, one of the most sophisticated aircraft on Earth, with stealth technology, advanced avionics, and weapons systems, costs $82.5 million. A NASA Extravehicular Mobility Unit, or EMU spacesuit, when you account for the original 1974 development cost of $15 to $22 million and adjust for inflation plus decades of refurbishment and upgrades, is valued at over $150 million today. But that's not even the wildest part. NASA spent $420 million developing the next-generation XEMU spacesuit between 2008 and 2021. And when the first 2 units are finally delivered, the total cost, including development and assembly, will exceed $1 billion. That's $500 million per suit. Per suit. Meanwhile, these aging EMU suits require constant maintenance under a contract with Collins Aerospace that costs $150 million annually just to keep 11 units operational. And of those 11, only 4 are mission-ready at any given time. 7 are in various stages of refurbishment. We literally have more fighter jets than working spacesuits. See, so what makes a piece of clothing cost more than a supersonic stealth jet? How can fabric and life support systems rival the price of cutting-edge military hardware? And why can't NASA just make more of them? Before we understand why spacesuits are so expensive, let's compare them to something more familiar: fighter jets. Because on the surface, this price comparison seems absolutely insane. An F-35 Lightning II is a marvel of modern engineering. It's a 5th-generation multi-role stealth fighter with a radar cross-section the size of a golf ball. It cruises at 1,200 miles per hour, carries advanced weapons systems, features cutting-edge sensor fusion technology, and can link with entire networks of aircraft and ground systems. As of 2025, the flyaway cost for an F-35A is $82.5 million. That's the price for the aircraft sitting on the runway, are ready to fly. Now, you might think, well, that's mass-produced. They've built over 1,200 of them. And you'd be right. Lockheed Martin delivered 191 F-35s in 2025 alone. The economies of scale are massive. Production is streamlined. Supply chains are optimized. But here's the thing. NASA's EMU spacesuits were also supposed to be produced in volume. In 1974, when Hamilton Standard and ILC Dover were contracted to build them, NASA ordered 18 units for the Space Shuttle program. The idea was simple. These suits would be modular and reusable. Astronauts could mix and match components to fit different body sizes. The suits would last 15 years, then be replaced. That was the plan. It didn't work out that way. Fast forward to today. Of those original 18 suits, 2 were lost in the 1986 Challenger disaster. 2 more were lost in the 2003 Columbia disaster. 1 was destroyed in a 2015 SpaceX cargo mission crash. That left 13 units. 2 more have been retired due to irreparable damage. We're down to 11. And of those 11, 7 require extensive refurbishment. That leaves just 4 mission-ready suits for the entire International Space Station program. These suits are now over 40 years old. They've exceeded their design life by 25 years, and yet they're still flying because NASA hasn't been able to deliver a replacement. This is where things get strange, because unlike fighter jets, which can be manufactured by the hundreds using established production lines, spacesuits are hand-built, one at a time, using materials and techniques that in many cases no longer exist. Many of the companies that supplied original components are out of business, and the carbon dioxide sensors used in current suits are no longer manufactured. The specialized fabrics? Some are custom-made in tiny batches, and replacing a single lost suit? Estimates range up to $250 million. What I'm about to reveal will completely change how you think about the engineering challenges of keeping humans alive in space. The story of how these suits got so expensive and why replacing them has been such a monumental struggle is filled with surprising twists, NASA controversies, and breakthrough technology that's happening right now in 2025. Hit that subscribe button because we're covering every major space technology development as it unfolds. And trust me, the next generation of spacesuits is unlike anything you've seen. Let's go back to 1974 when this all began. NASA awarded the contract to build the Extravehicular Mobility Unit to 2 companies, Hamilton Standard, now part of Collins Aerospace, and ILC Dover. Hamilton would build the life support backpack. ILC Dover would build the pressure suit itself. The development process was fraught with problems from the start. During testing, one prototype caught fire and seriously injured a technician. This forced a complete redesign of the oxygen regulator and circulation fan. When the first shuttle EVA was scheduled, an electrical failure in the circulation fan forced its cancellation. But eventually, they got it right. In 1982, NASA took delivery of the first operational EMU suits. These were revolutionary for their time. Unlike the Apollo suits, which were custom-fitted to each astronaut, the EMU used modular components. The hard upper torso came in different sizes. Arms and legs could be swapped. The idea was flexibility and reusability. The suits got their first major workout during the Hubble Space Telescope servicing missions. Astronauts used EMUs to perform some of the most complex repair work ever attempted in space. The suits performed brilliantly. Mission after mission, they kept astronauts alive. Then came the International Space Station construction era. From 1998 onwards, EMU suits were used constantly, assembling the station, installing solar arrays, replacing components. These weren't short EVAs. Some lasted 8 hours. The suits were being pushed to their absolute limits, but cracks were starting to show. Literally. In 2013, astronaut Luca Parmitano experienced a terrifying water leak inside his helmet during an EVA. Water filled his helmet, covering his eyes, nose, and ears. He couldn't see. He could barely breathe. He had to abort the spacewalk immediately and was in serious danger of drowning inside his own spacesuit. The investigation revealed that a contaminated fan pump separator had blocked a small orifice, causing water to bypass the system and flood the helmet. This component had been cleaned and reused, standard procedure for these aging suits, but contamination had been missed. NASA implemented fixes, but the incident highlighted a growing problem. These suits were wearing out. Components were failing in unpredictable ways. Parts were becoming scarce. And NASA's solution? In 2008, they initiated development of the next-generation spacesuit, called the XEMU, Exploration Extravehicular Mobility Unit. So why does a spacesuit cost $150 million when a fighter jet costs $82 million? Let me break down exactly where the money goes. Development costs. Unlike fighter jets, which benefit from decades of iterative design and massive production runs, each new spacesuit generation is essentially starting from scratch. The F-35 program built on F-22 technology, which built on F-16 and F-15 designs. There's institutional knowledge, established suppliers, and proven manufacturing techniques. Spacesuits? Every 40 years, we basically reinvent the wheel. NASA spent $420 million on XEMU development from 2008 to 2021 and still didn't have a flight-ready suit. Why? Because spacesuits face unique challenges that fighter jets don't. Custom materials and low-volume manufacturing. An EMU suit has 14 to 16 distinct layers of specialized materials. On the pressure bladder is urethane-coated nylon, gas-tight and flexible. Outside that is a Dacron restraint layer preventing balloon-like expansion. Then come multiple layers of aluminized mylar and Dacron for thermal insulation. Outer layers include Teflon-coated cloth, Kevlar, and Nomex for protection against micrometeorites, sharp edges, and extreme temperatures. Many of these materials are custom manufactured in tiny batches, specifically for spacesuits. There's no commercial market for space-grade pressure bladder fabric. Companies don't keep these materials in inventory. Each production run requires setting up specialized equipment, quality control processes, and certification procedures. The costs are astronomical. Compare this to an F-35, which uses materials like titanium, aluminum alloys, and composites that are manufactured at massive scale for multiple industries. The supply chains exist. The manufacturing processes are mature. The portable life support system. Here's where things get really expensive. The backpack, officially called the Primary Life Support System, or PLSS, is essentially a miniature spacecraft packed into a box you wear on your back. Inside this compact package, primary oxygen tanks holding gas at over 1,000 pounds per square inch. A sophisticated pressure regulator maintaining exactly 4.3 pounds per square inch inside the suit. A carbon dioxide removal system using lithium hydroxide canisters, or regenerable scrubbers in newer designs. A water circulation system for cooling. A sublimator that uses the vacuum of space to evaporate water and dump heat. A ventilation fan moving 6 cubic feet of air per minute. A two-way radio system. Heat telemetry and monitoring systems tracking oxygen levels, CO2 concentration, temperature, pressure, and water flow. And batteries powering everything for 8 hours. Every single component must work flawlessly in temperatures ranging from minus 250 degrees Fahrenheit to plus 250 degrees Fahrenheit. In vacuum, exposed to radiation. While being knocked around during physical work, there's zero tolerance for failure, because failure means death. The PLSS alone costs more to develop and manufacture than many entire aircraft systems. Testing and certification. Every spacesuit must undergo exhaustive testing. Thermal vacuum chamber testing. Underwater testing in the neutral buoyancy laboratory for hundreds of hours. Radiation testing. Materials testing. Human factors testing. Each test cycle costs millions of dollars. An F-35 undergoes rigorous testing too, but the test facilities exist. The procedures are established, and the testing can be parallelized across multiple aircraft. Spacesuits are tested one at a time using unique facilities. Maintenance and refurbishment. This is where current costs explode. Collins Aerospace holds a contract worth $150 million annually to maintain the existing 11 EMU suits. That's $13.6 million per suit per year. Why so expensive? Because maintaining 40-year-old equipment with obsolete components requires heroic engineering efforts. When parts fail, they often need to be reverse-engineered and custom-manufactured. Seals degrade and must be replaced with modern equivalents that match original specifications. Software needs updating to work with current ISS systems. Every 6 years or 25 spacewalks, an EMU must be returned to Earth for complete refurbishment. This involves disassembly, an inspection of every component, replacement of worn parts, testing, and recertification. It's like rebuilding a vintage car, except the car costs $150 million and keeps someone alive in the vacuum of space. But here's where the story takes an unexpected turn. Just when you think you understand why spacesuits are so expensive, NASA throws you a curveball. In 2021, after spending $420 million and 13 years developing the XEMU with no flight-ready suits to show for it, NASA's Office of Inspector General delivered a scathing audit. The report concluded that NASA likely wouldn't have 2 XEMU suits ready until April 2025 at the earliest, and by that time, the total investment would exceed $1 billion. $1 billion for 2 suits. That's $500 million per suit. That's more expensive than an F-22 Raptor, the world's most advanced and most expensive fighter jet, at $334 million per unit. NASA's response? They basically gave up trying to do it themselves. In June 2022, NASA awarded contracts to 2 commercial companies, Axiom Space and Collins Aerospace. The idea? Let private companies compete to build next-generation spacesuits. Axiom got a $228 million contract to develop suits for lunar missions. Collins got a separate contract for ISS suits. Axiom did something radical. They partnered with Prada, yes, the Italian luxury fashion brand, to help design the suit's outer layers. Engineers and fashion designers worked side by side. And in October 2024, they revealed the AxiomU, Axiom Extravehicular Mobility Unit. The suit features innovations NASA struggled with for years, and it fits anyone from the 1st to 99th percentile of human body sizes, solving the sizing problem that delayed the first all-female spacewalk. It has a regenerable carbon dioxide scrubbing system, eliminating disposable canisters. It includes bearings and joints for improved mobility. It can withstand the extreme temperatures at the lunar South Pole for at least 2 hours. And in July 2025, astronaut Koichi Wakata became the first human to test the suit underwater in NASA's Neutral Buoyancy Laboratory for 6 hours. Initial reports? The suit performed better than expected. But there's a problem. Axiom hasn't revealed the final per-unit cost of the AxiomU. And given NASA's own $1 billion development costs, industry analysts estimate each AxiomU could still cost $200 to $300 million once all development expenses are factored in. Meanwhile, there's a competing vision. In 2006, 5 North Dakota colleges developed an experimental spacesuit prototype operating at just 1 pound per square inch pressure differential instead of 4.3 pounds per square inch. Lower pressure means better mobility, easier to move, bend, and work. The entire prototype cost $100,000. Professor Pablo de Leon, who led the project, argues that NASA's insistence on 4.3 pounds per square inch is overkill. At 1 psi with pure oxygen, you're at the edge of safety margins, but the mobility improvements are dramatic. "We're making spacesuits too complex and too expensive," he told NPR in 2017. NASA's counter-argument? Safety. At 4.3 pounds per square inch, there's a comfortable margin. Any leak or malfunction is survivable. At 1 pound per square inch, you're right on the edge. There's no room for error. But this raises a question. Are we over-engineering spacesuits? Are we building fighter jets when we need pickup trucks? So here's what I genuinely want to know from you. Given everything we've covered, which approach do you think NASA should take moving forward? Drop your vote in the comments. Option A. High cost, maximum safety. Stick with 4.3 pounds per square inch. Full redundancy, no compromises, even if it costs $300 million per suit. Option B. Balanced approach. Maintain safety but simplify designs. Reduce costs to approximately $100 million per suit. Option C. Low cost, acceptable risk. Embrace 1 PSI designs. Dramatically improve mobility. Accept slightly higher risk. I'm genuinely curious what you think, because this debate is happening right now at NASA, Axiom, and Collins Aerospace. Your perspective matters. Maybe you'll identify a solution engineers haven't considered. The implications of spacesuit costs extend far beyond NASA's budget. And these suits represent a fundamental challenge for the future of space exploration. First, the Moon and Mars. The Artemis 3 mission, scheduled for mid-2027, will land astronauts on the lunar South Pole wearing Axiom U suits. But NASA's long-term vision includes regular lunar missions, a lunar base, and eventually Mars exploration. If each suit costs $300 million, and you need dozens of them for sustained operations, the math becomes impossible. Second, commercial space. Companies like Axiom, SpaceX, and Blue Origin are building commercial space stations. Private citizens are conducting spacewalks, like the Polaris Dawn mission in 2024, which used SpaceX's new EVA suits. If spacesuits remain $150 to $500 million each, commercial space exploration will be limited to billionaires and governments. Third, technological spin-offs. The life support systems developed for spacesuits have applications on Earth. Advanced thermal management systems, compact power systems, regenerable CO2 scrubbers that are being studied for hospital ventilators. But if development costs are prohibitively expensive, these innovations take decades to reach other industries. Fourth, the sustainability question. We can't explore space if we're spending $500 million every time we need a new spacesuit. There has to be a better way. Whether that's through commercial competition, design simplification, or breakthrough manufacturing techniques, the current trajectory is unsustainable. And finally, this connects to all of us. Every dollar spent on space exploration is a dollar that could go elsewhere. If we're going to invest billions in spacesuits, they need to enable missions that justify those costs, scientific discoveries, resource utilization, expansion of human civilization. Otherwise, we're just building very expensive clothes. But here's the hopeful part. We're actually making progress. Axiom's Axiom U completed thermal vacuum testing in 2025, exposing the suit to actual space conditions. It passed. Collins Aerospace is developing their competing design. Competition is driving innovation and could drive down costs. NASA's partnership with commercial providers is a game changer. When NASA tried to develop XEMU internally, they spent $420 million over 13 years with nothing to show for it. Axiom has delivered a working prototype in less time with clearer progress. SpaceX's new EVA suit, used during Polaris Dawn in 2024, demonstrates that alternative approaches are possible. While not rated for 8-hour lunar EVAs, it proves commercial companies can innovate in this space. And the lessons learned from these new suits will feed directly into Mars mission designs. Engineers are already working on suits that can handle Mars's thin atmosphere, dust storms, and longer mission durations. Science is making real progress. We're moving from an era where spacesuits were irreplaceable vintage equipment to treating them as manufacturable tools. The costs are still high, but the trajectory is improving. But spacesuits aren't the only space technology with shocking price tags. There's the James Webb Space Telescope, which cost $10 billion to build and deploy. There's the International Space Station itself, which cost over $150 billion. And there's the question of Mars missions, where a single mission could cost $500 billion. What if we could make all of this affordable? What if breakthrough manufacturing, commercial competition, and design innovation could slash costs across the board? If you want to explore these questions with me, subscribe and hit that notification bell. The future of affordable space exploration is being decided right now. Thank you for joining me on this deep dive into why spacesuits cost more than fighter jets. These incredible machines represent the pinnacle of engineering, personal spacecraft that keep explorers alive in the most hostile environment imaginable. Every seal, every valve, every layer exists for a reason. And yes, they're expensive, but they're also proof of what we can achieve when we refuse to accept limits. The next time you see an astronaut floating outside the ISS, remember, they're wearing a $150 million miracle that costs more than a fighter jet. And they're worth every penny. Keep looking up. The future is expensive, but it's also incredible. See you in the next one.